Hello, this is Jeff Hamrick at Rhodes College, and I'm going to talk about using the Fisher transformation to construct confidence intervals empirically for the true value of rho, in a particular case, that is. So I have here a set of data where the sample size is small. There are 15 cases in this data set. This is our temperature versus chirping frequency for crickets. And not only is the size of the data set small, but the sample correlation coefficient between air temperature and chirping frequency is actually quite high. When we build a randomization distribution for sample correlation coefficients under resampling, that is sampling with replacement, this distribution is highly left skewed, and it makes perfect sense why. Sample correlations are bounded between -1 and 1, and so if we're resampling from a set of data where the intrinsic relationship between, let's say, temperature and chirping frequency is quite high, these things are going to be mostly clustered at high values with an occasional rare example that tails off to the left like this. So if we use the switch trick in this case, our upper bound is most likely going to be above 1.0 and not have a very good interpretation for us. So there are two ways around this. You collect more data, that is, don't have 15 data points, have 250 data points, as in the Brigham Young University body measurements data set, or you use something called the Fisher transformation. So here's how we implement the Fisher transformation. This is not examinable for Math 111 this semester, so it's here for your education, but don't worry about it if you don't care to learn this material. What I'm going to do is I'm going to sample with replacement again, just as before, but this time the measure I'm going to define is not just going to be the correlation, but the Fisher transformation of the correlation. So first I'll compute the correlation of the resample, and then I'll compute the Fisher transformation of that sample correlation. The Fisher transformation again is 0.5 times the natural logarithm of 1 plus the correlation divided by 1 minus the correlation. Okay? So this is the sample correlation, this is the Fisher transformed sample correlation of a particular resample. I'm now going to collect a large number of these measures, where the measure now is not sample correlation, but the Fisher transform of the sample correlation. Let's collect. I'll go on ahead and pause the video and collect 1,500 of these, and then we'll have a discussion when we return. So we're done now collecting 1,500 Fisher transformed sample correlation coefficients, and we want to take a look at the distribution of those Fisher transformed sample correlation coefficients. Here they are. Notice that this distribution is certainly not perfect by any means, but it is somewhat closer to being normally distributed than this randomization distribution is. So I'm going to form an upper bound and lower bound on the confidence interval for this set of randomized values, and then transform them back to get a confidence interval in the space in which the original correlation coefficient is defined. So just bear with me for a second here and follow along. What is the Fisher transformation of our original set of data? Well, if I go right-click here and I add a formula, it's going to be 0.5, the logarithm of this correlation of 0.825358 divided by 1 minus this quantity. So that is the measure as taken with respect to the original set of data. That is the Fisher transform of the original correlation coefficient is 1.1734. So that's what I'm going to plot here on the Fisher transformed randomization distribution, and see it's roughly in the center right here. In part 2 of this video, we'll compute the lower bound and the upper bound, and then undo the Fisher transformation to get a confidence interval for the correlation coefficient, not the Fisher transformed correlation coefficient.